Okay, so picture this. NASA is getting ready to send its Phoenix lander to Mars, to the frozen Arctic plains. And they have one huge goal: follow the water. But to do that, they needed a very special kind of sensor. So who do you think they called? Not geologists, not astronomers, they called soil physicists. Yep. They needed people who understood the really intricate dance between water and dirt right here on Earth, so they could help find it millions of miles away.
And you know, that mission to Mars really brings us back to a super fundamental question right here at home. Whether you're a NASA scientist looking at the red planet or, just someone curious about the world, the answer is always the same. You look in the soil. Because water, as scientists like to say, is the lifeblood of the soil. It pretty much runs the show for every biological, chemical, and physical thing that happens just beneath our feet.
So let's get into it. In this explainer, we're going underground to explore the hidden world of soil water. We are going to crack the code on its two most important properties so we can finally get what's really going on in the ground we walk on every single day.
All right, let's start with the most basic question you could possibly ask. How much water is actually in the soil? It sounds simple, right? But getting that answer is the first, absolutely crucial piece of our puzzle.
Scientists have a pretty straightforward name for this: volumetric water content. The easiest way to think about it is like this. If you have a box, say a cubic foot of soil, what percentage of that box is just water? That's it. It's the simplest, most direct way to just quantify how much water is there. What's really amazing is how our ability to measure this has just exploded over the years. I mean, the classic method is super simple. You grab a soil sample, you weigh it, you bake all the water out of it in an oven, and then you weigh it again. The difference in weight? That's your water. But today, wow, we have satellites circling the planet, mapping soil moisture everywhere. We have things called cosmic ray neutron counters and fiber optic cables giving us data in real time. It's just an incredible leap. And this isn't just theory. At sites just like this one in Oklahoma, scientists are constantly testing and comparing all these cutting-edge gadgets. And all this effort is for one reason. Knowing how much water is in the soil is critical for basically everyone, from farmers to people who predict the weather. But here's the twist. That's not the whole story. Not even close. So knowing the quantity of water, that's one thing. But to really solve our puzzle, we need to understand its behavior. And that, my friends, is a much deeper mystery. This right here is the central puzzle that just knowing the water content can't solve. I want you to imagine two pots of soil. Both have exactly 30% water content. In one pot, the plant is happy, it's green, it's thriving. In the other, it's wilting and dying. How on earth is that possible? The amount of water is identical. So what's going on? Well, the answer comes from a concept you probably remember from a high school physics class: potential energy. Think about a book. A book just sitting on a table has some potential energy. But if you lift that book up in the air, you've given it more potential energy. And if you let it go, what happens? It naturally falls back to the table. It moves from a state of higher energy to lower energy. Water in the soil works the exact same way. This idea is called soil water potential. It's basically a measure of the energy level of the water. And just like that book, water in the soil always moves from an area of higher energy to an area of lower energy, always. So it's not just about how much water is there, it's about where the energy is telling it to go. Now, a really, really crucial part of this whole thing is something called matrix potential. Just think of it as the grip or the suction that the soil particles have on the water. So let's go back to our poor wilting plant. The problem was never the amount of water. The problem is that the soil it's in has a much tighter grip. It's holding onto that water so fiercely that the plant's roots just can't pull it away. Okay, so now we have our two key concepts. We have water content, which tells us how much, and we have water potential, which tells us how tightly that water is being held and where it's going to go. When we put those two together, we can finally crack the code of a soil's true character. Think about this for a second. I'm sure you've felt this. You can walk on the wet sand, right at the edge of the ocean, and it feels firm under your feet. That's because the sand grains are big and they just don't hold onto water very tightly. But the fine, mucky soil around a pond, it's a swampy mess. The soil particles are tiny and they cling to the water for dear life, creating that soggy disaster. That is matrix potential in action. So scientists map out this behavior using a tool called the soil water retention curve. You can think of it as a unique fingerprint or a personality profile for every single type of soil.
This graph shows you the water content versus the suction or metric potential. It tells the complete story of how that specific soil deals with water, how much it can hold, and how easily it lets it go.
Let's use this to compare a couple of different soils. See the loam? That taller bar on the left? It shows it can hold a ton of water. Now look over at the sand on the right. It starts with less water to begin with, and then its curve just plummets. That steep drop means it gives up its water super easily, with just a tiny bit of suction. That's why the beach feels firm. The loam, on the other hand, holds on much, much more stubbornly.
But just when you think you've got it figured out, the story gets even stranger. A soil's relationship with water isn't actually fixed. It behaves differently depending on whether it's in the process of getting wetter or drying it out. It's a wild phenomenon called hysteresis. You could almost say the soil has a memory.
And one of the main reasons for this is something with a great name, the ink bottle effect. So imagine an old-fashioned ink bottle, right? It's got a big, wide body and a skinny little neck. Well, the pores in soil are a lot like that. They're this complex maze of wide chambers all connected by narrow little tunnels.
Okay, let's break down how this works. As the soil gets wetter, water flows in through those narrow necks, but it might not be enough to fill up the bigger bottle parts. But then, when the soil starts to dry out, those skinny necks hold on tight to the water, and they basically trap the water that's inside the larger pores. And the result of all that? A drying soil holds on to more water at the same suction level than a wetting one does. It actually remembers that it was full of water. So we've gone from these tiny, microscopic ink bottle pores all the way up to the planetary view. Let's zoom back out and see why having this deep understanding of soil water is so unbelievably critical on a global scale.
This quote really just nails it. All of this science, all of this data we're collecting, it isn't just for dusty, old academic papers. The whole point is to turn this knowledge into tools that help us live better and, manage our planet a little more wisely.
So, at the end of the day, why does any of this matter? Because when we understand soil water content and potential, we can build way better models for forecasting floods and for monitoring droughts. We can predict wildfire risk with so much more accuracy, we can help farmers use their irrigation water way more efficiently, and we can manage our planet's most precious resource, water.
And that brings us right back to where we started. From NASA trying to figure out a spoonful of Martian dust to see if life could exist, to us, right now, using satellites to map water across the entire planet, the basic science is exactly the same. Understanding the secret life of water in the soil is fundamental to understanding and protecting our own world.
So the next time you walk on a beach or water a plant in your house, just remember that the ground beneath you isn't just dirt. It's this incredibly dynamic system, and it's telling a story of energy and memory and life. The only question is, are we listening?